Hello everyone and welcome to HDL for Digital System Design. I'm Dr. Mike Brovchek. It is a pleasure to have you all here watching this video series. So we're going to dive right into perhaps the biggest misconception that we have in this space. So without further ado, here are the slides. So biggest thing here that we need to really start to consider is that we need to start thinking about um, the central idea of writing code that describes hardware. So first off, I want to address a huge misconception that is probably the biggest one that people have. It's likely that you already know a programming language. C, Python, Java, doesn't really make a difference. You'll think about perhaps reading or writing Verilog, which is the language we're going to be using to describe our hardware systems, in this very top-down, top-to-bottom like way. When we think about code in general, we usually think about executing line by line, and that's something that we need to kind of unlearn or at least explore in a different way when we talk about writing code that describes hardware systems. So the instinct of going line by line is definitely wrong, so we're going to try to break you of that. So if that's the one thing that I can ask you to focus on for these first couple videos, just remember that when we write code for hardware, it is very different than when we write software for a typical processor. All right. So here we go. Hardware versus software. Left side, we've got some software. We have A equals B times C, or B plus C, and D equals A times 2. On the right-hand side, the equivalent for hardware description in Verilog, we essentially have an assign statement there. So assign A equals B plus C and D equals A times 2. So in general, the same idea, but the difference is that when we think about software, we definitely think linearly, right? Line 1 will execute, we'll finish, and then we'll go on to line 2. That's very different. In hardware, both of these things, the A being B plus C and D being A times 2, they both describe hardware that exists and functions at the exact same time. So yeah, on the hardware side, there's basically an adder that works, right? That is the A equals B plus C. And there's something that's shifting, essentially shifting a value by 2. They're always active, right? So the moment B changes, A and D both will change through some set of real physical hardware and gates. So what are the big 3 differences here between software and hardware description? So one is execution. In software, most of the time we're thinking sequentially, one thing at a time, right? Hardware side, concurrent. Everything happens at once. The assignment of things. When we talk about assignment in software, we are talking about taking some set of values or operations and assigning them to some storage space to basically compute or to store on, right? So A equals 2 is essentially we are storing the value of 2 into that variable A. We're literally storing that and computing on that. When we make an assignment in hardware, it is actually forming a connection. When we say A equals something, that something is now fused in terms of what is going to happen, right? It is forming a structure instead of this logical space of storage. And then this last one, the idea of time. So in software, there's behind the scenes some program counter, right? There is some mechanism that advances a clock that says, okay, now we will work on the next operation, and then the next operation, and the next operation. And a piece of software running on different systems is going to operate at different speeds because of how fast it can run, but it still is going through this very sequential, one instruction at a time process. Now, yes, there are multiprocessor systems and all these other things, but that is doesn't change the fundamental idea of one operation at a time. Okay, compare that to the hardware side. Everything that we talk about is explicit, right? There are delays that are based off of hardware. There's a clock that's actually running. The how things behave is now explicitly defined. It is no longer based off of an abstraction like a program counter that we normally are used to in software. So that is something that we're definitely going to have to deal with. So let's look at this from maybe an analogy standpoint. You can think of software as like a recipe, right? A step-by-step, do a task, move on to the next one. So if you look at our example from before, you could do A equals B plus C. So you compute something, then store it. So you're going to do that computation of B plus C, store that result into A. Then you're going to move on. You're going to go and you're going to say, okay, D equals A times 2, whatever A was, right? In the previous step, you're going to use. And now you're going to store that result, or you're going to use that result, in which case, here, this one we're going to print. If you think about the hardware side, we have both this adder and shifter, right? A equals B plus C is the adder, and the shifter is D equals A times 2. They both exist at the same time. The order of these assignments really doesn't matter, right? They both exist at the same place. So what does that mean for us? Well, what it means is that if we look at this over, I'll say, a timeline, right? We're not looking at specific units of time. But if you look at this, imagine that on the software side, you have some values for B and C. You could go through and one step at a time compute what the values are being stored for A and D. Basically, you can see that if we use 3 and 4 as that example, after we execute line 1, the value of A will be 7, D will have no value. Afterwards, after we go to the next line, we'll get A remains to be 7 and D is 14. Now, on our other side, right, when we provide inputs for B and C into this system, what ends up happening is both the A and the D value will get values after some amount of settling time, but they will get values at every instant in time, right? There is no disconnect here. There's no, this happens essentially for all time. Now, when we are writing and developing software, we're basically writing instructions. When we are writing and describing hardware, we're no longer writing instructions. We're talking maybe more about the topology, the how this river, how these things connect with one another. And so that's really a different way to explore and to be developing code when we are trying to describe hardware. So now there are a bit of nuances here, and we will explore a lot of this over the next couple weeks. It is important to note that when we say that operations are concurrent, it doesn't mean that they are instantaneous. So in our previous examples, if a value like B were to change, what happens is that computation, the adder for A equals B plus C, since A relies on B, and if we change B, there's some amount of time that that adder takes to propagate, right, for that value to actually become correct. And so that time does impact how long or when we can compute D, right? Because if A is changing and D requires A, there is some amount of time that is required between these two events. that we have to take into account. So there is delay. Every gate that we use, every gate that we will use, has some amount of delay. It's called propagation delay. How long does it take from an input that is changed for the output of that gate to have the value that's expected? Normally described in nanoseconds or picoseconds. It is also important to note that wires can add delay, just in terms of how long a wire is and how much time it takes, or how much how much time it takes for that charge to distribute. It does impact timing. And the delays do add up. So the path, right, between a change and the eventual output, each of those gates and wires between those gates adds some time that we need to account for. So what I was showing in the previous slide with essentially those outputs did assume that we were in a steady state, meaning that all of these delays had propagated through. It's important to note that while those delays are propagating through, things could be glitchy in the middle, but that's all taken care of in terms of our timing expectations. So just know that when we see truth tables, in general, we are going to be talking about the steady state, not the transient, meaning not the time between things. So just the steady state. All right, so remember, concurrent does not mean instantaneous. Rivers, they flow in parallel, but it still takes time. All right, so why does this matter? Most of the time for now, we're gonna be just fine in terms of we'll wait long enough, right, for the river to settle, meaning that we aren't going to be doing things with very fast timing constraints, but it will impact how fast we can operate our devices over time. So you can think about the time between, say the start and end of the river or the segment you're looking at. All the things you want to do in there, basically, the more things you want to do, the longer the total amount of delay, the total time it will take to get between all the inputs changing and your final output. And so that is, if you look across your entire design, the longest of these ends up creating what we call a critical path. So we will talk more about this over the next couple lectures, but just know that the longer your path, the slower your overall speed of your device can be. So big things to just remember now. Gates add small delay. Delays accumulate. When we look at a truth table, that is for steady state, not the transients, not all the switching in between. And we will see how clocks play a bigger role in this, more towards the back half of the course. So just know that some of our tools will give us some of these details and some of this information, and we will definitely take a look at that again towards the end of this course. All right. Remember, more code equals more hardware in general. So in a software side, you might do an operation and the system reuses the same component some way, right? So you could think of even multiplication could be repeated addition. Or if you had this example of x equals a plus b and y equals c plus d, you're going to reuse the same adder in your CPU. If you write the same thing in Verilog, assign x equal to a plus b and assign y equals c plus d, that is two adders. That is not one adder. Cannot reuse the adder. That is two separate adders. So more code, more hardware when we talk about writing hardware. So in general, right, and again, there's some hand waving here, but more lines of Verilog, more gates, more FPGA resources. You cannot just delete or malloc a flip-flop, right? So in a C program, you can remove things, right? You can clear and free memory. You cannot do that when you're talking about hardware. Once you synthesize and create your device, it is fixed. All right, but we get parallelism for free. So here's an example. We have assign sum equals a plus b, product c times d, and then a result of sum or product. So all of these three operations happen at the same time. No threads, no cores, no need to synchronize between these. So we get parallelism by default. If we wanted to do things sequentially, it actually takes effort. All right. So one of the things that we really do need to talk about is, there's clearly advances in artificial intelligence, large language models. And again, you should leverage those. You should use those to help supercharge what you do. But using them without understanding the underlying expectation of, or seeing, using them without thinking about what you expect to see is pretty dangerous. So something you might do, right? Ask some LLM, right? Your favorite LLM. Here's some Verilog with multiple assign statements. In what order do they execute? So you could do this, right? You could ask an LLM that before you actually get a response. Predict. So go ahead and predict. What do you think? What do you think is going to happen if you have multiple assign statements? What order do they actually execute in? All right. So put it in, get a response from um, whatever LLM you're using. If you have a good AI model, right, it should tell you that all three are concurrent. Now, if you've got a terrible model, for whatever reason, it might actually give you an answer that says, hey, these operate from top to bottom. No matter what, you want to compare your prediction to the output, right, and reflect, right? Basically, this will give you an understanding in this particular case of the quality of the model you're using, right? If it says top to bottom, you probably don't want to be using this model for things, right? Because it clearly doesn't understand writing. Writing in Verilog is different than writing in other programming languages. So, in general, if you go through this process, you'll either be able to determine some discrepancies between your understanding and AI model's understanding. That's the goal here. Or you might be able to use it to evaluate the quality of the model you're looking at. Regardless, it is important that you continue to check the responses you're getting from these machines, from these tools. Okay, so written out here explicitly, consider this a litmus test, right? Use it to basically figure out if you're going to use this AI model for your work. Now, we're using it in this way here, but in the future, you might use it to assess other things about either the machine, the LLM, or yourself. Okay, so big takeaways. Verilog describes concurrent hardware, not sequential instructions like you're used to. Assign statements, those are going to create permanent connections. It creates a wire between two things. In general, more Verilog means more hardware. Once you dedicate a resource at synthesis time, it is fixed. You cannot remove it. You get parallelism for free. Doing things sequentially is actually super hard. You could think again that you're describing the geography of the river, not writing a recipe. All right, so up next video, we'll look at synthesis versus simulation. Thank you all.